Hello, good evening, good afternoon, good morning, wherever you are. Right, this is all about stress and strain and Young's modulus on the top there, look. And then we've also got a modulus of rigidity. These are all very important in mechanical principles, science and materials, and in life in general. So the first thing is stress. So stress is force over area. I put direct stress there because we're talking about direct stress in the first part. So all stress is really is force over area. And that's the symbol for stress, like that weird thing there, like Greek symbol as force over area. Obviously force is measured in newtons and area is measured in meters squared. It's meant to be in M. Don't do millimeters, right? Don't do inches. Not in America. Right? Newton per meter squared, or that works out, we'll use a Pascal. But it's the same, newtons over square meter Pascal. We'll use Pascal, which you may have seen in a previous life, or you will see in future workings. So force over area. So you all come across stress. If you remember in school or college, if you did a belly flop onto a swimming pool, if you did a belly flop, it's going to hurt you because you've got more area, because you've got your entire body slapping onto the water. So the stress is going to be a lot. That's why you feel it. But if you do the same thing and you dive in, so you sort of head first, and you're decreasing your area, you don't feel as much stress. The same force, because gravity is pulling you down at the same amount, but because your area is less when you dive in, you feel a bit less stress. So stress is force over area. And then that stress will cause a strain. And strain is just change in length over original length. So this will come clearer now when we do some more examples, or it may already be clear to you, depending on how much you've read. So change in length just means how much something's been squashed or pulled apart, or so change in length is the change, so that's squashing or pulling apart, and the original length is how long this thing was originally. So that's the strain. So a stress causes a change in length, and if there's too much stress, too much change in length, things break. So this is the symbol for strain, epsilon. Delta L just means change in length, and L means original length. You may see delta L as X. It's just a length, how much this thing has been squashed by or stretched by. So stress and strain. Stress is force over area, strain is change in length over original length. Because it's a length over length, there's no units. There's no units for strain. No units for strain. As long as you're in the same units, you can be in what you want. So with this one, you can be in millimeters over millimeters, meters over meters, inches over inches, miles over miles. Makes no difference because you're in the same units, so the answer will be the same. I always suggest you go into meters anyway, because that's the SI unit. But when I'm doing this, sometimes I'll go into millimeters sometimes, because especially if the change in length is so small, it's a bit easier to do it in millimeters. So here's a bit more. So here's my metal square bar. It's got a length of 500 millimeters, which is 0.5 meters. Just don't forget, there's 1,000 millimeters in a meter, so that's what you're doing. Half, look, 0.5. Now this here, now when we're doing force over area, because stress is force over area, the force is easy because it's just how much newtons we've got pulling on us. But the area is this area in here. It's the cross-sectional area. And in this case, I've sort of zoomed in, it's 30 by 10. So if you cut this with a knife, that's the area you'd see. So that's the area you want to use. Now in this case, it's like a rectangle, 30 mil by 10 mil. So it's going to be this area, which you should all know is going to be 30 by 20. Now we can't be in millimeters. I suggest you convert into meters first. Don't work it out and then divide it by 1,000, because that's wrong. So 30 millimeters is 30 divided by 1,000. So you need to convert into meters first. So you can do this, look. Do that. 0.03. Or that. So you can either do 0.03 or 30 times 10 to the minus 3. So if you wanted to convert millimeters into meters, so because we've got 30, if you put times 10 to the minus 3 on the back of it, it's the same thing as dividing by 1,000. Quick way of doing it. So 30 millimeters is 0.03 of a meter, and 10 millimeters, so do the same thing, like 10 you can do this way, it's 0.01 of a meter. So before you do the area calculation, make sure you convert into meters. Right? 0.01. Now, so don't do this, right? Because you know there's 1,000 millimeters in a meter. What people do is, and what some people will do, they always do it, they'll do this. So this is going to be the area, 30 times by 10. 30 times by 10, right? So this is going to be the area. So that's the area in square millimeters. And then people just divide it by 1,000. You can't divide that by 1,000 because that's just the length. You need to divide it by 1,000,000 really, because you've got 1,000 by 1,000. So what you should do is convert into meters first, then you can do this. So the area, the square area or the rectangular area of this metal bar is 0.03 times by 0.01. 0.01. So it's 0.03 times by 0.01. All in meters. Thank you very much. Press equals, you get that. You can either do that. Don't let it 10 to the minus 4 because that's not engineering. So that there is the area of this bar in square meters. So that's the area you use. It's the cross-sectional area. So now we've got that, right? We can work out now stresses. So the first one we'll talk about is tensile stress. And tensile strain is still going to be force over area because it's just stress, and it's still going to be change in length over original length. Now, tensile is pulling apart. It's like your Stretch Armstrong things. When you pulled it apart, it will stretch. So when something's in tension, it's been pulled apart. So for example, here's my metal bar. It's the same metal bar as this. It's just head on now. So I'm pretending that this metal bar of cross-sectional area 300 times 10 to the minus 6 and length 0.5 meters is being pulled apart. Right, we'll just do one direction at the moment, unilateral. Right, we'll just do the X direction. It's been pulled apart this way by 4 kilonewtons. So it's in tension because it's being pulled apart. Tensile force going that way. That force, right, is going to make this thing stretch by 5 mil. Whatever this thing's made out of, this 4 kilonewton force is going to make it stretch by 5 millimeters. So this dotted line here, this here is meant to be it being stretched. So this is the stretchy bit. It's been stretched. Change in length is 5 mil. So it's been stretched by 5 mil. The original length was 0.5. So we need to work out the tensile stress induced in this metal bar due to this force. And we know that stress, tensile stress, or stress, is force over area. What's the force? 4 kilonewtons. Don't forget the K. What's the area? It's the cross-sectional area here. That area there, which is 300 times 10 to the minus 6. So that's what I'm going to put in here. I'm doing force over area. So the force is 4 kilonewtons, or 4,000, divided by 300 times 10 to the minus 6 equals all that numbers. You can put all that in, but I would press E and G to round it up, not round it up, but put it into engineering format, because you may miss a 3 out. So we'll do this. 13.33 megapascals. Don't forget 10 to the 6 is mega. 10 to the 6, like megabyte, megaton, 10 to the 6 is mega. So you could still write this. You could still do 13.33 times 10 to the 6. Nothing wrong with that. Or you could do mega. That's the tensile stress in that bar due to that force. Stress is always big. Mega. Right? If it's small, if you get small, there's something wrong, right? Especially when in mechanical principles. So you need to make sure that you put in 10 to the minus 6 and 10 to the 3. That's the tensile stress. That's how much stress is pulling this apart. Now, this tensile stress and this force is causing this thing to stretch by 5 mil. So we need to work out the tensile strain, which is linked to change in length. Obviously, if this thing keeps pulling, it's going to snap in the end. So tensile strain is just change in length over original length. There's no units, and I'm going to keep in meters. So 5 millimeters, which is the change in length, is 5 divided by 1,000 meters, like we did before. So 5 divided by 1,000 is that. Look, 5 times 10 to the minus 3 divided by the original length, which was 0.5 meters, because we're going to stay in meters. 0.5. That's the strain. 0.01 strain. No units. Now, normally you measure strain with a strain gauge, because it's quite hard to measure a small change in length. So if you know the strain, you can work backwards then to find the force and whatever. So that's the strain. Now, I've kept it there in meters, which you should always do. But like I mentioned before, as long as you're in the same units, it doesn't matter what you do. So for this one, I'm going to keep it in millimeters, because you get the same answer. So 5, which is the change in length, divided by original length, which is 500 mil in meters, get the same answer. So as long as you're in the same units, top and bottom, you'll be alright. Just get into the habit of converting things into meters, because that's the SI unit. But it would work if you were both in inches, miles, kilometers. It's a length over a length. That's tensile stress, force over area, tensile strain, change in length over original length. Tension is pulling apart. So something's in tension, it's being pulled apart. Next one is the opposite way. So this is tension, something being pulled apart, and the other way is compression, something being squashed. Compression. If you're squashing a can, you're crushing a can, you're compressing it. So you're squashing it. If you watch a bit of rugby, and sometimes you get like if they run into a tackle, they compress their neck, so they get a stinger, which just means your neck muscles are being squashed, compressed. So compressive stress is still force over area, and compressive strain is still change in length over original length. It's just going the other way. One's making this thing bigger, and one's making it smaller. So compression is really squashing. So you're squashing a can. So here's your can. If this can was in tension, you'd be pulling it upwards and making it bigger in the Y direction here. When you're a can crusher, you crush it, so you make it smaller. You're compressing it. Still the same formula, force over area, change in length over original length. So here's our bar again. It's the same bar. I'll use the same bar because we can use the same area. So in this case, it's being compressed by a force of 5 kilonewtons. So it's the same area as before. Look, I've used the same bar. So it's been squashed by 5 kilonewtons, and this change in length is meant to be it's being squashed. So it's in compression, not tension. It's been squashed by 10 mil due to this force. So we need to work out what is the compressive stress. Same formula, force over area. What's the force? 5 kilonewtons. Divide by the area, which is still this 300 to the minus 6. Gives me that 1666666. You can put that in, or you can press this 16.66 times 10 to the 6 Pascal, or you can put mega. So that's the compressive stress. Now, if you're wondering, when we go a bit further, to differentiate between compressive and tension stress, tensile stress is positive. So if we were going to add these up, we would put a plus in front of this because it's tension, it's getting bigger, it's going in that direction, which we call plus, and compression's going that way, so we'd call it minus. So we would put a minus in front of that, because we could be adding these things together, so one's going up and one's coming down, so that's why you'd put a negative number, but that's in the future. So compressive stress is 16.6 megapascals in that direction. Don't forget, it's been squashed. The compressive strain is still the same, change in length over original length. It's been squashed by 10 millimeters, and it's 0.6 or 600 mil long. I'll keep it in meters again, look. So we'll do, so 10 divided by 1,000, that gets that into meters. Thank you very much. Divided by the original length, which is 0.6, divide that by 0.6, 0.0167. No units, because it's a length over length. Alright, just to show you again and get the same answer, I'll keep everything in millimeters. So 10 millimeters divided by 600 millimeters will give us the same answer. As long as you're in the same units, it's alright with strain. It's a length over length. I would keep converting into meters though, because of the SI unit, as I keep saying. As long as both lengths are in the same units, it is okay to use millimeters. Because there we are, like I've just done. Because sometimes, especially with this type of stress and strain, the change in length is very small. So I can picture 10 millimeters better in my head than I can this. I can picture 10 millimeters better in my head than 0.01 of a meter. So sometimes I use millimeters when I'm doing strain. So compression is negative, tension is positive. That's how you differentiate. Compressive strain is negative because the change in length is negative. It's going that way, isn't it? That's how we differentiate between tension and compression. One's positive, one's negative. So that's stress and strain. It's the same formula, it's just depending on which way it's going. So these are linked by a thing called Young's modulus, and this really is how stretchy a material is, the elastic modulus, elasticity. So stretchier, stiffer, obviously you don't use these words because they're not scientific, so it's elastic. So obviously some materials, you can stretch more materials. You can stretch some materials more than others. For example, acrylic or plastic, copper, you can stretch copper. Obviously acrylic is a form of plastic, right? So you can stretch plastic more than you can stretch a metal. And diamond is very hard to stretch, it's very stiff. Obviously copper is easier to stretch than steel. Now you can tell this by this. The lower the Young's modulus, the stretchier or more elastic the material. So for example, acrylic or copper, right? Acrylic has got lower Young's modulus than copper, which means acrylic is stretchier than copper. Whereas copper has got 117 gigapascals and diamond has got 1220 gigapascals. So diamond's very stiff. You can't really stretch diamond because it's got a really, really big Young's modulus. So that's how it's linked. It's how much stress you need to change the length of a material. You need a lot of stress to change the length of diamond. That's why it's got a high Young's modulus. You don't need a lot of stress to change the length of plastic or acrylic. So Young's modulus E is stress over strain. That's all it is, stress over strain. So it's this stress we've worked out over the strain. So that's a symbol, E, capital E, symbol for stress, symbol for strain. So in materials, we'll probably do a graph like this, but this is stress strain graph. And the steeper the curve, right, the higher the Young's modulus, because here's your stress. So you need a lot of stress. So this is high stress here to stretch. Don't forget, strain is linked to change in length. So this is really equivalent to a very low change in length. Obviously, with acrylic, you don't need a lot of force or stress to stretch it a lot, because strain is linked to change in length. So if you do materials, the steeper the line, the steeper the straight line on a stress-strain graph, the higher the Young's modulus. Luckily, all these values are in a book for us, or we can look them up, so we can reference them. So stress over strain is Young's modulus. So for example, in our example up here, we've got 13.3 mega and 0.01. So if I wanted to work out what the Young's modulus of this material is, I can now do stress over strain, and the stress was 13.3 mega. See if I can put on there. Yeah. And the strain was 0.01. So this will now give us the Young's modulus. You can write all that down, but you might forget a few noughts, so press ENG. 1.33 gigapascals, which is a plastic. You can look that up, and there's plastics below 3.2. So if you look up what material has got a Young's modulus of 1.33 gigapascals, it's ABS plastic, or that range. So you can look things like that up, so you can work out the Young's modulus and perhaps even identify what type of material it is by the number you get. Or you could work out, if you know how much stress you're applying to this material and you know the Young's modulus, you can work out the strain for failure. So Young's modulus is how stretchy something is. The higher the number, the stiffer or the less stretchy the material is. This has got to stop doing that. This has got quite a low Young's modulus, so it's quite stretchy. It's got a plastic material. So that's direct stress, that's compressive, and that's tensile stress. The other stress we can have is shear. Same formula, force over area. Strain is change in length over original length. It is the same formula, it's a slightly different way of looking at it. Because shear stress is like when you cut your hair. When I shave my head, I'm shaving my head. So shear really is this. One force going that way and one force going that way, and it shears off there. That's why we use bolts and rivets, because they're good in shear. So this could be two plates with a bolt or a rivet in the middle of it. There's a force going that way and a force going that way. So this bolt is in shear. See if I can get it. This bolt is in shear there, because that's where the joint is. So if this force is too much and this force is too much, the bolt will shear off. Right, that's why we have bolts and rivets to keep two bits of metals together. If the force is too much, it can shear off. Shear, not shear. If anybody spells it like this, I'll go nuts. Don't spell it double E, it's EA. So shear stress and shear strain. So it's still force over area, but it is slightly different. For example, here's the way we look at it. So if I had a rubber block like this, and it's stuck to the ground like that, the area in shear is the area stuck to the floor. The area is the area stuck to the floor. So it's that green bit there. It's this green bit here, look. I've just coloured in red. So, and it's also, if you're doing a bolt, it'll be the area of the bolt. So a bolt is normally round, so it'll be the cross-sectional area, because that is the area in shear. Obviously, the bigger the bolt, the better it is in shear, because you've got more area to cope with it. And the more bolts you have, that's why we put loads of rivets of bolts in things, because the more bolts you've got, the more area you've got, so the better you are for shear. And the thing's not going to fall apart. But if I had a block like this, stuck to the ground, it's 30 millimeters this way and 10 millimeters that way. The area in shear is the area stuck to the ground there, look. So the area in shear is shaded in green. Obviously, it's a rectangle, so it's going to be 30 by 10. 30 by 10. Obviously, we can't be in millimeters because we've got to be in meters, so that's why I'm doing this. Just don't forget, there's 1,000 millimeters in a meter, so you can do this. So 10 divided by 1,000 times by 30 divided by 1,000. This will give us the area in meter squared. 300 times 10 to the minus 6. So don't just multiply 30 by 10 and divide that by 1,000. You've got to convert the lengths into meters first, and then you'll be fine. You can do it this way. If you want to do it this way, 30 millimeters times by 10 millimeters, alright? That's going to give you 300. 300, because we've got 1,000 there and 1,000 there. 1,000 times 1,000 is a million. So you've got to divide this by 1,000 by 1,000, because you've got 1,000 by 1,000, which will give you that. So you can do it that way. 30 by 10 gives you 300, and then if you add 10 to the minus 6 on the end, that would be cool. Don't do this, which people will do, because everybody does. 30 times by 10, they do that, and they go, well, Morgan told me there's 1,000 millimeters in a meter, so I'll just divide that area by 1,000. But you can't do that, because you can't. That 300 is an area, not a length. So just convert into meters first. So that's the area we're going to use when we're doing force over area. Another slight difference is this. If I've got whatever this is, a rubber block, and it's fixed here, so it can't move, it's fixed, it's 40 mil high, and I've got a force coming this way, I'm pulling it this way, it's going to go like that on the squint, because this force is going to make it go like that. So it's going to sort of sway that way, it's going to be deformed that way. So this is the change in length. So that force there is going to cause this rubber object to deform like that, or sway like that, or deform like that. The change in length is the difference between there and there. Itchy nose. So the change in length is that difference there. It's nothing to do with this length here. It's nothing to do with this length. It's to do with this bit here. Because the taller, so if you've got a tall building in the wind, a tall building is going to move in the wind. A shorter building is not going to move so much in the wind because it's not as high. So if I made this 40 mil higher, if I made this 400 mil, it's going to deform more. The force is going to make it go this way more because it's higher. Like trees in the wind will move. A tall tree will sway more than a bush, won't it? of a small tree because of the height. That's why that's the original length. The 40 mil is the original length, and the change in length is how much it moves by. So you need to keep an eye out for that. Don't do this length here. So for example, in this one above there, we've got now shear stress. What is the shear stress on this rubber block? So the symbol for shear stress is that tau. It's like a weird T. Still force over area. So the force is 2000 and the area is 30 by 10, which is this. So that's the shear stress. So we do 2 times 10 to the 3. We'll divide that by 300 to the minus 6. Shear stress. Thank you very much. Oh, devil number. 6.667 times 10 to the 6 megapascal. That's shear stress. So if this thing was being pulled, if this block was being pulled by 5 kilonewtons, sorry, 2 kilonewtons, the shear stress in it is going to be force over area. The force is easy. The area is the one you need to look out for in this example. It's the area stuck to the floor. It's that area in there, which we know is 300 because we've worked it out. 30 times by 10 in meters squared. So that's that one. Is slightly different. You just need to make sure you get the right areas involved. The shear strain, there's a symbol for shear strain, dodgy Y, is still change in length over length. But in this case, the change in length, the change in length is this thing here, this distance in here, which is 0.5 of a mil, and the original length is how high the object is. So the higher this is, that's the original length. So that's the original length, that's the change in length. In this example, I've kept them both in millimeters. So the change in length is 0.5 millimeters divided by the original length, which is the height of this thing, which is 40, gives me that. 0.0125, no units. So you need to be careful. This is the original length. The height is the original length, and how much it deforms by in that direction is the change in length. I've kept it in millimeters here, but it makes no difference. I could do that in meters, so I could do this. So I could do, so 0.5, so divide that by 1,000, which gives me that really. So that's 0.5 millimeters in a meter, divide by height, 40 mil. So we'll divide that by 40 times by 10 to the minus 3, because it's the same thing. If you divide something by 1,000, you'll get that. Press equals 0.0125. So as long as you're in the same units, you'll be laughing. So here's my thing. So a tall building will move more in the wind than a building closer to the ground. So bridges, like a suspension bridge, the Severn Bridge, when you've got the big stanchions, they will move in the wind because they're quite high. Right? A small little bridge is not going to move much because the height is less. So this height is less. Skyscrapers, they do move. Right? They do move. But a skyscraper will move more in the wind than your house will because the skyscraper is higher. So that's what you need to think about when you're doing shear stress. Shear stress has got a very similar thing, right? Something that's got low shear stress is very rigid. So it's the modulus of rigidity. So tensile and compression is elasticity, modulus of elasticity, and shear is how rigid something is. So the modulus of rigidity is G. You can look it up in a book. So how rigid or stiff a material is. It's the same formula, shear stress over shear strain. That's the formula in Greek. Right, they're the symbols. So it's the same thing, shear stress over shear strain. Same thing as Young's modulus, stress over strain, stress over strain. This is tension or compression. This is shear. So shear stress over shear strain. For example, if I wanted to work out the modulus of rigidity of whatever this material is, I've got the shear stress and I've got the shear strain, so I can work that out because it's stress over strain. Shear stress is that and shear strain is that, which we've just worked out up by there. So one over the other. So we can do 6.67 to the 6. We'll divide that by 0.0125. That will give us, press E and G, 533.6 megapascals of modulus. Keep going if you want to look, keep going. So that gives us that. Now then, rubber is not very rigid, look. So rubber is very low. So tungsten is not very, it's very rigid. Steel is very rigid, look. But copper is not as rigid as steel. So the higher the number again, the more rigid it is. So the lower the number, the less rigid. So tungsten is very rigid, rubber is not very rigid. You can bend, you can move rubber, can you? It's a bit of a rubber block, you can bend it a bit. Tungsten's quite hard. So this material here is 533.6 megapascals, which is in giga, because we can compare it here, look, so that's going to be this, 0.5336 to the 9. Let's just check that. Yeah, so 533.6. So 0.5336 to the 9. So that's the giga, because 9 is giga. So 0.533, so it's below copper and it's above rubber. Rubber is very low, look. So you could look that up and see what it is. So that is Young's modulus, modulus of rigidity, shear stress, tensile stress, compressive stress. You will come across this quite often in science and materials, in engineering, so you need to be aware of it. Obviously, there's more to it than this because we're only considering forces in the x direction. You've also got y as well. So, but that is that, over and out. I hope you weren't stressed too much. North Star.